In a previous example, we had a flat plate, and essentially what we were doing was we were calculating the friction drag on the plate for both incompressible and compressible flow given a laminar boundary layer. But now for this problem, what we want to do is we want to do the same thing except calculate it with the turbulent boundary layer, because then we can compare the difference and see how drastic the drag is, which as a spoiler, it's pretty drastic. So up in the top right corner here, we can see a velocity of 100 meters per second for a laminar boundary layer gave about 175.6 newtons of friction drag. Now, for a velocity of 1,000 meters per second, so definitely creeping up way beyond that incompressible point of Mach point 0.3, we had a drag of about 5,026 newtons. So now what we're going to do is pretty much the same process, except we're going to calculate the friction drag for a turbulent boundary layer instead. And also up here are all of the free stream numbers, and then the surface area, and then chord length that we'll need throughout the problem. So for part A, we're going to start out with a free stream velocity of 100 meters per second. And now in order to determine whether it's incompressible or compressible, we're trying to see is the Mach number either below or above that 0.3 kind of a pivot point. So for our free stream speed of sound, so that's going to be the square root of gamma times the gas constant times T infinity. And then plugging in the values, we should get 340.2 meters per second. So then for the free stream Mach number, that's going to be V infinity divided by A infinity. And then that should give 100 divided by 340.2. That should be about 0.29. So we're just underneath that incompressibility to compressibility pivot of 0.3 Mach number. So we should be safe to assume that we are in non-compressible range for air. So now the next step that we'll have to do is calculate the Reynolds number. So for Reynolds number of the chord, that is going to be the density, or the free stream density, times the free stream velocity times the chord length, divided by the free stream viscosity. And then from the previous example, just plugging in the values above here in light shaded green, we got 1.36 times 10 to the 7. And then with this in mind, we can calculate the coefficient of skin friction drag for a turbulent boundary layer. And now here we're going to want to use the total version of the skin friction drag instead of the local version, because we're accounting for the entire chord length of the flat plate. So we can say that CF is going to be equal to 0.074 divided by the Reynolds number of the chord to the fifth power, or 0.2. And then from here, we should get 2.77 times 10 to the negative 3. And then now what we can do is we can calculate the friction drag. So that's going to be equal to 1/2 rho infinity V infinity squared times S times C sub F. So I'll just plug in the values here real quick. So density is 1.225 kilogram per meter cubed. And then V infinity is 100 meters per second squared. S is 40 meters squared. And then CF is 2.77 times 10 to the negative 3. And then from here we should get a skin friction drag of 675.9 newtons. But now we're going to have to multiply this by 2, because the total is going to have to account for both the top and the bottom of the plate. So we should get a DF total of about 1,352 newtons. Now from the past example, using the laminar boundary layer, we had 175.6. So in the end, so if we have 1352 divided by 175.6, that is about a 7.7 times increase in drag just for using turbulent flow versus laminar flow. So then now we can start looking at B. So for B, so our free stream velocity is going to be 1,000 meters per second. And then A infinity is going to be the same because temperature hasn't changed. So we'll have 340.2 meters per second. But then our Mach number, or our free stream Mach number, is certainly going to change. So that's we'll have V infinity over A infinity. So we'll have 1,000 divided by 340.2. So that'll give us about 2.94. And then the Reynolds number, we can actually do something a little bit sneaky, where we don't have to recalculate it. We can simply multiply it by 10. So we'll get 1.36 times 10 to the 8. And the reason we can do this is because our Reynolds number, it consists of, so density isn't changing, and then temperature isn't changing, so our viscosity isn't changing either, because they relate to one another through Sutherland's law. And then the chord length, that's not changing either. But here, the velocity is, but it's increasing by a factor of 10. So we can simply just multiply 1.36 times 10 to the 7 by a factor of 10. And then, so that just saves a little bit of time from calculating. So then, pretty much what we can do is we can find C sub F. And now the reason we needed Mach number and we needed our Reynolds number is because with turbulent flow, we have to use this graph to estimate what our coefficient of skin friction drag is. So if we grab a pen here, so we have a Reynolds number of about 1.36 times 10 to the 8. So I'm going to estimate it's about here-ish, give or take. And we have a Mach number of about 2.94. So we're going to be halfway-ish there, give or take. So what we can say is for the coefficient of skin friction drag, that could be about, let's say, 1.34 times 10 to the negative 3. And then from here, now we can calculate the skin friction drag. So it's going to be d sub f equal to 1/2 rho infinity v infinity squared times s times c sub f. So I'll just plug in the values here real quick. And we'll have 1,000 meters per second now for v infinity. And then we'll have 1.34 times 10 to the negative 3. And then that should give us a friction drag equal to 32,700 newtons. So then we can say that dF total, so that's going to be equal to twice dF. So then we'll get a dF total equal to about 65,400 newtons. So that is definitely a large increase compared to the laminar boundary layer from before. Because if we divide those two, then we get about a 13 times increase. See, I really like this example because I feel like it's a good way to not only relate incompressible and compressible flow, but also to show the difference of just your friction drag alone, just from having either laminar or turbulent flow. Because with turbulent flow, you have all those viscous effects and then added drag. So you can definitely see it in the final results between both the laminar and the other, because we had, 7.7 times increase, and then now a 13 times increase once we get past that incompressible range into the compressible range. So it definitely matters just what speed your aircraft is going at for essentially designing, your different parameters and such. I know we're using a flat plate, but depending on your airfoil, you could approximate. So definitely a good thing to keep in the back of your mind for your aerospace toolbox.